for me to dive in now?
Yeah, we can start.
Okay, great. Yeah, thank you so much for having me, and thank you for the introduction, Divi. Yeah, my name is Ben. I'm a software engineer at Snowflake. Um, yeah, apologies. I am not a researcher, so this will probably be much less academic than some of the other presentations, but I think it's a good view into a real deployed production system with some interesting research components as well. Okay, so let's get started.
Ben, can you guys hear Ben okay?
It's a bit
Okay.
quiet.
Yeah. Huh?
It's a little bit.
Yep.
Sound okay?
Yeah, it's okay. Ben, if you can speak a little louder, that'll be great because I'm in a classroom where I don't know if there are external speakers or not. I'm basically projecting the sound from my laptop.
Oh, yeah, sure, no problem. Yeah, I'll do my best here.
Great.
Okay, so yeah, the agenda for today, most of the content is coming from this paper. We have, yeah, I guess drafted up last year, and we're going to present at ACM Sigma, the industry's track later this year. There's also an accompanying blog post you can check out if you're interested. But yeah, the agenda, I will start off with a high-level overview of like Snowflake's AI products. This AI SQL component is one of the first ones that integrates directly into the SQL query language and the core database products that Snowflake has been working on for the past like decade plus. But there's a lot of other newer features that build on top of it, including like information retrieval components as well as agentic workflows. So I'll briefly touch on those and close with some of the newer stuff on the agentic side. But the bulk of today's topics will be on the AISQL, SQL database layers. We'll talk a little bit about the architecture in it'll be pretty abbreviated and simplified, but we have at least a few diagrams on that. Most of the paper's contents are on some of these performance optimizations we're doing and how to update the query language to handle LLM workflows. And yeah, we'll close out with some of the newer projects on the agent side and some Q&A. Okay, so this is very timely. Sigmod has awarded Snowflake's original paper, which is about 10 years ago, the Test of Time Award. This paper was written by our founders and a large number of other co-authors. This is a very good, I guess, we've come a long way since this paper has come out. I think Snowflake just missed like the Kubernetes and Docker containerization changes. So it's interesting to see how things have changed and how our newer systems, which are all containerized and running on microservices, especially anything involving GPUs, and how these two interface. We'll dive into this a little bit. So I've tried to kind of readjust some of the diagrams or discussions that we've had in our paper, which is for a slightly different audience, to be a little bit more consistent with this paper. But this paper is a lot of interesting history from where Snowflake was and how it became a tens of billions of dollars business. And I think one thing I saw rereading this paper recently is a kind of a fun fact. At the time of publication, I think in 2015-ish, they report being very proud of having a few petabytes of data in the full like databases. Now we're at a few exabytes about 10 years later. Okay, so Snowflake Cortex AI, this is a super high level overview of like the AI offerings at Snowflake, just to kind of give a landscape of what Snowflake provides. At the very high level, there are a number of agentic workflows, both ways for companies to create their own agents. So we handle things like memory and chat history and compaction or summarization for long sequences, as well as a first-party agent that Snowflake provides called Snowflake Intelligence that makes it very easy for customers to interact with their data stores, including lots of metadata on knowing which tables are relevant, which tables have foreign keys across different databases and schemas, and things like that. In the middle layer, we have a number of information retrieval components. So there's both products for structured data as well as unstructured data. So Cortex Analyst kind of directly maps a natural language question into SQL, into the existing SQL query language for tables that have extracted data. And there is also a more generic Cortex search product, which is sort of like a combination of both keyword searches as well as embedding stores for like document retrieval. And then finally, at the very bottom of this like cake, we have a fewer lower level components, one for handling document processing. So you can embed, parse, and extract from PDFs. And then finally, we'll talk about Cortex AI SQL, which is the SQL integrations for LLM requests. Okay. So Cortex AI SQL, this is probably one of the oldest products at Snowflake that integrate with the LLMs. Most of it started with this very simple mapping operation. Uh, we have exposed a very simple, low-level kind of tool for power users where you can create any system prompt and apply it to your tables, to your data that's already in Snowflake. So this is mostly handling text use cases, but it does also handle images and other file types. Yeah, so the interface allows you to choose a model. We basically support all of the frontier models, so OpenAI, Anthropic, um, Mistral, others. For a long time, we were using primarily Llama models, self-hosted, but it's increasingly moving towards OpenAI and Anthropic just because they are just, yeah, moving so quickly and outperforming the other models. The prompt interface, this has changed a little bit. In this example, there's just a like string concatenation operator, but we have changed this to like a templating format that makes it easier for you to it's just a cleaner interface for string manipulation. And this can also support file data types. And then finally, yeah, you point this operator at your table and columns that you're interested in. This is the SQL interface, but we are also expanding very, very quickly into Python and REST APIs. And the REST API has actually overtaken the SQL use case just in the past few months. There's some very large like power users that are making the bulk of their requests through REST and not Snowflake, or sorry, not SQL. But yeah, the SQL use case is interesting because it does handle almost all of the batch use cases. Um, cool. Okay, so there's a few other operators here. AI filter allows you to handle a predicate to filter your data sets. And yeah, again, this is all using natural language and it can be applied to various file types. So instead of having to extract a column for, extracting a column using like a trained classification model, whether a customer is satisfied, you can now zero shot an instruction very easily. And this same operator can be applied to joins. We'll talk a little bit about how we make this more performant than the naive use case. But yeah, in the worst case, this is an O of NM like cross join. And yeah, ruins a lot of these LLM operations. And we'll talk a little about how we skip some of those whenever possible. And then finally, we have an aggregation function that allows you to take an entire column and apply a instruction to it. And this can be quite complex and multi-step operations like identify personas across of these customer reviews and then suggest new products for each of them and things like this. It doesn't have to be a singular summarization task. It can be very, very complex. Um, okay, diving a little bit more into how AI ag works, I think the paper talks about one of our older strategies where we had a few different stages of operation where we were doing some like extraction phase, we were combining, and then at the end we were summarizing. Since the paper has launched, we've made a couple changes just to simplify the number of system prompts we're managing. All the prompts come with uh, quite a bit of like management and overhead, especially as the winning frontier models change every 3 to 6 months. So we've dropped one of these stages and kind of converted it into the simplified flow with only two types of operations. So at the very top of this tree structure, you have all of the user data, and these need to be chunked based on the LLM context window. So this is a pretty important hyperparameter for us. the larger these chunks are, the more time you spend in attention, which grows, which grows n squared in the length of your input. But if you have very, very small chunks, then it's harder to, for each of these first LLM map operators to like get a sense of the distribution of the input. It might only look at like a very local slice. And it also means that you're making many, many more LLM calls. So this becomes a really important parameter for both execution time as well as the quality of the output. But the very first step here is that we'll take this chunk of data, which should contain a large number of rows, although if the rows are enormous, it could be a single row, and perform some map operation that takes this generic user instruction. In this case, it's summarize the top insights from these news events. I'm sorry, lost my.
So Ben, the question on the map reduce thing. So why do you have multiple levels of reduce?
Yeah, so our goal with reduce is to take a large number of these map operate, like the output of the first chunking step has a one-to-one output response where it's going to take the user instruction and apply it to a subset of the data. If this data set is huge, then there could be like 10,000 of these map operations, or there could be 10 or 100. But at some point, there'll be enough map operations that will run out of context window to do it in a single reduce operation. So that's all this reduce is doing, is that it runs as many times as it needs to with the constraints of the like LLM context window that we support.
I see. And should I look at the map operators as being identical, but they're working on the sharded parts of data? Is that how I should envision that?
Yeah, I think that's a reasonable way to describe it. I mean, the main goal is that we can't process this entire data set in a single LLM execution. So we're going to chunk or shard or distribute it in some way. And how that ends up happening is almost random. I mean, we have a large number of workers streaming this data set in parallel, and they will basically try to greedily grab as much as they can up to the context window or this parameter we've set for the max input data size, and then run an LLM request on each of them.
And do the LLM map, are they programs or are they themselves also models?
Probably the simplest way to describe it is that it's really just a very simple system instruction and a single LLM invocation. Yeah. And then our goal is just to recursively reduce these until we have a single aggregate result. Yeah, so that's AIAG. That's sort of like a low-level power tool, similar to Complete, but that allows you to to aggregate across an entire column. And to be honest, in some ways, this may be deprecated by some of the newer agentic, like this is a very rigid workflow that we've sort of hard coded, but an agent may be able to accomplish something similar now. But this predates a lot of that by a couple of years. At least Snowflake's, usage of agents in that capacity. But it's very similar. This is just a hard-coded workflow to handle this task. So here's a little bit more of a concrete example for a general business use case. Someone would like to know what is the yearly revenue growth and market outlook for companies that have recently undergone a CEO change in the renewable energy sector. So there's a bunch of components to this request. There is a filtering step that is checking, has a company had a CEO change and are they in the energy sector? And we can do this with a very generic prompt system instruction, basically copy pasting this natural language request. And then we'll run our aggregate request across these filtered data sets using this like summarize insights instruction. And then we'll also do a bunch of joins using AI filter to identify like the reports that apply to this company. And this is all in the existing SQL language where we have access to group bys and common table expressions and things like that. Okay. So let's talk a little bit about the architecture of how this works under the hood. Um, so before we dive into this, can kind of highlight what how we thought of this problem before we started thinking about the solution. So some of the main things here that the execution nodes that actually handle the SQL like queries, they're optimized for all the CPU bound tasks that traditional SQL queries were doing, generally joins and simple arithmetic, and they are very poorly optimized for anything based on GPUs. What makes this a little bit more challenging as well is that almost all of the bulk workloads, especially the workloads that are generating a significant amount of revenue, tends to be quite complex. And that means that it's very hard to estimate things like cost and selectivity in the query compiler. It's only once the query reaches the execution nodes that they actually have access to data in tables, and things like selectivity can only be estimated online. And once this thing is already starting to process data, so it has to be done with streaming algorithms. And yeah, and this means like uh, query plan optimization before execution time and pruning isn't really possible for this use case unless you have a very like dynamic treat-like structure that is not something Snowflake really supports at the moment. And yeah, I think 90% of the queries run on Snowflake have, sorry, 90% of the queries run in Snowflake with using the SQL, the LLM operators uh, have only a single row. However, something like 90% of credit consumption comes from very large queries that run more than an hour and have tens or hundreds of thousands of rows. And for a traditional SQL query, tens or hundreds of thousands of rows are pretty trivial, but invoking an LLM that often, this becomes extremely expensive. So there's also lots of cost and budgeting constraints or requirements there that these queries are very, very expensive. Some of them are hundreds of thousands of dollars for a couple of hours of execution.
Wow. So the the LLM access is the model running on the like Anthropic site or or OpenAI? So you are really going out to them and getting the results, retrieving the results from them.
Most of the time, yeah, yeah. There was a while where, I mean, we still continue to host, self-host lots of models, especially like the Llama family models, but increasingly the best models are at OpenAI and Anthropic. We'll either call the first parties directly, or a lot of times we'll call Bedrock, which is also hosting them. But yeah, they will go across the internet to their clusters often, especially. Yeah. That is, I think, the common case these days now.
I see because you have a you don't have visibility on the LLM component, so query optimization becomes extremely hard. But
Yes.
if you do a repeated execution of the query, can you hand tune the query or optimize the query? Are there ways to do that? I mean, is that, you gather statistics so that the next time around you can basically redo the query using some optimization?
Yeah, we don't have stateful components like that on the SQL side today. A lot of the LLM calls have a extra. We treat the query history as customer data, and that makes it very difficult for us to I don't know, do a lot of an analytics on. There's other components I talked about earlier. We're talking the AI SQL runs at the SQL query level. There's other features that are more like, the agents for how you talk to your data and how you use natural language to generate queries. Those will have lots of historical data about like which tables are most relevant, what are common patterns to filter and join across multiple tables. And those parts will have access to query history and can kind of improve or generate like golden queries or examples of like an optimized query. But at this layer, we don't do much like that. Yeah. Okay, but here is a kind of a high level architecture of how we are calling LLM inference. And yeah, a lot of these requests end up going to OpenAI, Anthropic, and Bedrock. There are some self-hosted models. But all of our users will go to a multi-tenant global service. And by the way, this slide is going to use slightly different framing or terminology from the original Snowflake paper. Um, our paper, yeah, is written for Sigmod and is more consistent with the Snowflake papers. But these slides, I have put together a little bit closer to how we describe and think of the systems in production. So they're much less academic, but closer to reality, I think.
So
Um,
what does multi-tenant LLM inference mean? Does that mean from a user query perspective, you can use different models or something like that? Is that what means?
No, it's less about the types of models the user has access to. Like there are fine-tuned models, but those will be very tightly scoped to, a fixed number of GPUs that other customers cannot access. The main consideration here is that the GPUs are a extremely scarce commodity, and that their throughput is really, really valuable. So customers that have traditionally required data to live in kind of their own like private warehouses and didn't want that interacting with other accounts at all, those constraints are not necessary in the GPU environments. So a lot of times the GPUs will batch up requests to maximize the available memory they have. Those requests will combine data across different accounts, even if the accounts typically require that data be separated. And that's purely just to maximize the throughput and ensure that the GPUs are running as hot as possible all the time. So there's lots of really interesting, I mean, kind of undesirable side effects here is that, we expose stochasticity parameters like temperature and top P, and things like that. Because that batching is done across accounts, that the execution order of a LLM request is going to change all the time. So even if a customer is setting a temperature equal to 0, they shouldn't expect the results to be the exact same every time. If it gets batched in a different way, it is going to affect the output as well.
That makes, from a user's perspective, this non-determinism must be problematic, right?
Yeah, definitely. We have some caching components that help address this, but yeah, it's not ideal. But the GPUs are they're so valuable that this is kind of a compromise, I think, we're making. Okay, so these green nodes, these come directly from the original 2016 Snowflake paper. The global service is multi-tenant, handles all of the query planning. It is disjoint from these execution nodes that break down a query into parallelizable components. And it's only the execution nodes that really have access to the data storage. And the execution nodes are scaling independently from data. Um, um, if the query contains an LLM component, then it will call an external function, basically a HTTP or gRPC request to this Cortex component, which is our internal name for this routing part. And that will ultimately call some GPU in some cluster somewhere. Um, Something that's interesting about the warehouse size is that dictates the number of nodes that a query will receive. And that impacts directly this like request parallelism component. So how many calls are being made to this Cortex LLM router in parallel? Generally, that type of work calling LLMs are going to be GPU bound, and we have lots of rate limiting and fairness constraints. So even if you have 64 workers, it will probably get rate limited to something as if it had fewer workers, but it does still help the CPU bound components. And working in this existing SQL interface and global service and execution platform, we get the benefits of all the existing SQL components. So there's caching layers, there's constant folding, things like that. But these blue nodes, Cortex and self-hosted models through VLLM are really the only parts that are, I guess, owned by Snowflake. A lot of these other things are either existing, like the green stuff, or going to third parties, like the yellow nodes.
So the Snowflake self-hosted model, is it something like Llama or is it in-house?
It's both. Yeah, I think Llama was a very common use case maybe 2 years ago when this project first started. There's also a suite of in-house trained models, especially I think our Arctic embedding models are very competitive. There was a while we even tried training our own large language models, but the costs were exorbitant. So we only did that a few, 6 months and then stopped. Um, so okay, diving a little bit more into the Cortex LLM routing components. Um, LLM routing consists of it contains some optimizations for high availability. So many of our users are not prescriptive about which provider they want to use. As long as they provide a model and it's hosted by any of these, it can end up going to any of these providers. The requests are mostly stateless, so it makes it easy to kind of redirect traffic as necessary for availability. But that is changing increasingly with like content and memory. There's like a containers API as well, and then all that adds statefulness to these requests, and that makes it harder to like dynamically change the routes here. But the first like step of this flow is that SQL is going to call Cortex and do some LLM pre-processing. So for the examples I gave earlier about AI filter and AI ag, and there's another function AI classify. These are essentially just like prompt registries where we are giving like a managed system instruction that concatenates or works with the user's data and whatever natural language instructions they provide. So those are living in the same environment or the same like servers that handle GPU execution. So before the SQL node attempts to schedule or execute the LLM inference, it will first call these services to generate these prompts. And that once you have the generated prompt or the generated like raw text instruction, that makes it much easier or makes it even feasible to estimate the workload size. So this first step about LLM pre-processing is mostly about getting the size of the work that is going to be executed on GPUs. And there's also some optimization here that we can check a response cache. So if there's an exact match for this row, it's just an O of one key value store lookup. We can skip the GPUs entirely. But then after, we'll filter this on the cache misses and sum over all of the tokens that we've returned from the pre-processing step. We have a very good estimate of the work size, and then we can send this to the scheduling and pacing units. So from the previous slide, we talked about there is a degree of parallelism component that impacts the number of queries or requests running in parallel for a single like user request. This pacer step will help kind of manage that for fairness and for higher availability across a large number of like concurrent workloads from different customers so that one user doesn't negatively impact all of the others. And yeah, from there, they'll basically go to this query performance database and get an allocation of how much pace or tokens per second that this query has access to. And then it'll get pushed onto these queues at that rate. These queues have some constraints. So the first thing is primarily which model is the user requesting or is Snowflake assigning for this query. But another one is some features like zero data retention. That can also be basically a filter on which routing environments are viable. And so if a provider is not providing zero data retention and a customer requires it, they will not be allowed to serve traffic on that instance. Yeah, there's also considerations for cache-aware routing to improve the prefill prefix cache hit rates. So we'll try to ensure that for a given query, especially with a large system instruction, that it routes to the same set of GPUs. Yeah, that part is mostly handled automatically by the providers for prefix caching. The VLM will also try to take care of this as well. Cool. Okay. Let's talk a little bit more about some of the other performance optimizations we're doing. This one's a dense slide. So predicate reordering. So I'll start in the kind of the top right. There's an example query where a user is trying to call summarize ag to summarize specific papers and join it with the relevant images and filter on papers that are describing TPCH benchmarking system. So this slide shows two query plan graphs for both of. I mean, they're executing the same query, but have different tree structures for how to execute them. And the raw data sets contain 10,000 papers and 100,000 images. So as we flow upwards through this tree or through this graph, we're going to have a variety of different filter and join operations from this query that are all associative and commutative. And so we can reorder them however we see fit to execute this as quickly as possible. But our main goal is to minimize the GPU cost. That is just so much larger than anything that a traditional SQL query has done with CPU execution. On the left, we have a naive implementation. So in the worst case, you may end up executing 110,000 LLM invocations. You'll run your expensive AI filter on every single paper. You run another expensive AI filter on every single image, and then do the cheaper CPU-bound executions last, and then finally join. I guess one of the main things that we had to change when we were shipping AISQL is to reorder these predicates to treat the external functions that are calling LLMs as if they are basically infinitely expensive or at least significantly more expensive than any CPU-bound task like joins. So this task on the left has a tiny join cost, but the call on the right we really care about is minimizing the LLM cost. So it is on the right, plan B, the query optimizer is identifying that there's a CPU-bound filter that should be executed first, and then the expensive LLM image filter is pulled up above the join. So we're doing the join earlier. It's much more expensive, but this drastically reduces the number of LLM calls.
If you can you explain how the left-hand side is doing 110,000 LLM calls and the right side is only doing 330 LLM calls? Can you just go over it? I just want to understand that.
Yeah, of course. Yeah. So, and this is also a little bit of a contrived example, but this is the kind of the worst case on the left is the 110,000 LLM calls is that we can start from the bottom, the leaf nodes are raw data sets. And so there's 10,000 papers and 100,000 images. The very first operations that occur in plan A is filter AI prompt abstract and filter AI prompt image. And so we are doing the most expensive LLM calls on the entire paper data set, that's 10,000, and then another expensive LLM AI filter call on 100,000 images. So those two combined add up to the 110,000 LLM calls. And then we'll do a cheaper CPU-bound filter, and then finally a join. So the join cost is tiny. It's 3 times 2, 6, but the LLM cost is 110,000.
So on the left-hand side, what has happened is you have reordered the filters so that you are basically doing the filtering first on the years when the paper appeared. So that reduces to 10,000. It still does 10,000, but then it filters about 300 papers there. So at the 10,000 is still, how do you say that on the right-hand side, only 330 LLM calls? You still have the 10,000 calls, right?
There's still 10,000 AI filters, but the main difference is that we've pushed down the CPU date filter, and we've just artificially said, oh, out of 10,000 papers, only 300 of them passed. So the selectivity was 3%.
So essentially, the filter is sent to the LLM call itself, so that LLM is going to filter out a very, at the source itself, they're going to be filtering out. Is that what happened?
How I would describe it is that the order of execution is that we don't care which filter occurs first, but we do want to ensure that we save the most expensive tasks for last. So if there's two filters in this query, there's three filters in this query. One is on the abstract, one is on the image, and one is on the date.
Yeah.
The date filter is the cheapest one. So in plan B, we'd like that one to go first. So we scan all 10,000 papers. This is papers P and images I. We want to look at all 10,000 papers and only look at the dates. And that is super cheap. I've ignored it from this slide in terms of the cost. I'm only tracking LLM costs. So that's like, I'm treating that as if it's free. And then it had a selectivity of 3%. So there's 300 passing papers. And then after that, we do the AI filter on only 300 passing papers.
Okay.
I have a question. So when you select a date, like scanning the date, you just don't use LLM, like you just use regular method to scan the date of the paper?
Yeah. So in this example, I'm assuming that there's already an extracted column p.date that is just an integer value. And so that's a super cheap CPU task. This example is a little bit contrived. So it kind of asserts a lot of like assumptions about the structure of this table. But the main point is that we've changed the optimization strategy from joins to minimizing joins to minimizing LLM cost. Okay, let's move on. So this is another optimization we're doing on specifically for AI filter, where we are treating the AI filter as a binary classification task. So for every row, we want a positive or negative predicate outcome. So one thing we're doing to improve the speed here is through model cascades. So over the course of the query, this really only applies for a large query where there's enough data to kind of dynamically learn the quality of a smaller proxy model. Let's say it's an 8 billion parameter LLM against a larger Oracle model, say a 70 billion or 450 billion parameter model. So yeah, we have some strategies here for learning in real time or learning online rather, the thresholds for passing and failing, as well as a wide uncertainty region for stuff in between. And for these benchmark data sets, we can get a pretty significant speed improvement with a minor degradation in accuracy.
Can you explain what is adaptive cascading? I mean,
Yeah, let me see if I'll jump ahead to this slide, might be more useful. Is that we have a normal query will execute all of these AI filter calls with, let's say, a Llama 70B model. But we also have access to a much smaller 8 billion parameter model. We can reduce costs and increase performance if we use the smaller proxy model, the 8 billion parameter model, as often as possible. So for a query that has a large data set, let's say it's at least 10,000 rows, we can execute both of them in parallel and see how often they're aligned with one another and kind of dynamically learn what is the confidence interval we need. So both of these models may output like a log probs basically, or a threshold, a score that asserts, yes, this should pass, or no, this should not pass. We want to figure out at what scores output by the proxy model do we have alignment with the larger language model. And if they are aligned, then we can reliably use the smaller model in place of the large language model and save a lot of cost. Like, in that example, it might be 50 times faster and cheaper to use a 8 billion parameter model over a 400 billion parameter model. So over the course of the query, we'll execute both and try to find these scores that we have confidence that the low quality, the smaller model has the exact same result, as well as the scores that we don't have enough confidence to trust it reliably with the like accuracy or F1 or precision recall requirements that we've set as basically as hyperparameters. Um, so yeah, there is a separate paper for this that my colleagues Pavel and Kyle have just published a couple months ago about how they do this, including some of the key components on online calibration. Um, and this is a reference here. Does that make sense? Sorry, I don't know if this is too hand wavy or.
So I guess what I'm gathering is that basically the adaptive cascade that you're saying is you run the query in parallel on two different models of a smaller model which may be less accurate, and based on that you make a decision or something. Is that the idea?
Yeah, you could think of kind of this is all an online algorithm, so it is dynamically changing over the course of the query. But you could think of the early stages of the query. We're trying to learn what are the appropriate thresholds for the small model, the proxy model. And then at some point, we have enough confidence that we have enough data that we can start to call the proxy model exclusively and skip calls to the large model, at least if the scores are below or above these thresholds.
And you're running these, you have a, so on this graph, there are multiple data sets that you are looking at, the Cora and IMDb and things like that. So that's the data sets, but what are the set of queries that you're running? Is there some benchmark queries that you are running in each case?
So these are just an evaluation of how this method performs on a benchmark data set. But the production use case is that a user is conducting a query like this. And let's say we care about maybe the images part because there's 100,000 and this needs to learn these thresholds. So it doesn't work at all if you only have, say, 100 rows. But a user can execute an arbitrary query like this. And we would use a proxy model to quickly determine can we handle these AI filter components using a smaller model?
And do we know what percentage of user queries end up using the proxy model versus the real model, the bigger model?
No, I don't have that. Sorry.
Okay, yeah, okay, thank you.
Okay. Last performance optimization I have from this paper. I think this is, yeah, there's a very specific case we can identify for joins where if we can identify that one side of this join, let's say it's n in this example is small and the cardinality is less than, let's say, 1,000 rows, then we can rewrite this query from a join where it's doing this cross product O of mn LLM requests to a classification task. So instead of asking, does each of these rows map to each of these categories with one call per per pair, and this and include a very large system prompt that's often 200, 300 tokens long, we can do a single LLM invocation that asks, is this classify this movie into one of these n categories so that we can execute the LLM request for this entire right side in a single LLM shot, and do this in only O of M LLM requests. And it significantly reduces the number of LLM calls from O of MN to just O of M. So we're only doing one LLM call per review on the left side. This is one thing that's really nice about this performance optimization is that if this is a task where the outcomes are mutually exclusive, this actually not only has a very large impact on execution time, it actually also improves the F1 score. So there is one of these data sets is looking at NASDAQ stock tickers and trying to map, I think, a description to the stock ticker of a company. And some of them can be very ambiguous. But if you have a list of all of the possible candidate categories, it's much easier for the LLM to identify which one is correct rather than doing just a pairwise estimate on every single one in isolation. So for the NASDAQ data set, we see a huge improvement in the F1 score going from about 5% to almost 80%.
If I want to understand what's happening in this technique is, if you go back to a slide, you go back to this, essentially what you're saying is that instead of sort of doing the join by doing the, for every row, you go to the LLM and then do the join on LLM. What you're doing is you're populating the categories table on the database side, and then using that to perform the join kind of locally. Is that right?
Yeah, I think that's one way to think of it. Maybe another way to describe it is that instead of asking like, this first row is this movie was great, and then we have all of these 7 categories. Instead of asking this movie was great, is this a movie category? And then having a second LLM query that asks this movie was great, is this a books category? And then doing this again for is this an entertainment? Is this a TV? Is this a hotels? Is this a vacation? And that ends up costing you something like 2,000 to 3,000 tokens of system prompts because it's always repeating the exact same like 200 token system prompt for each of these pairwise attempts. We can do the entire review row against all categories in a single shot, saying we change the prompt basically to this review that says this movie was great, classify it into one of these 7 candid categories: movies, books, entertainment, TV, hotels, vacation. And that only has a single system prompt rather than 7.
Thank you.
Cool. Okay. So that's kind of on the SQL side. I will say a lot of the work on the SQL side is kind of wrapping up, and that there is a lot of new developments on both the REST API as well as on higher level agents that use these SQL interfaces. So there's a lot of new products that basically just make it easier to avoid writing SQL, and even specifying the exact tables that you're interested in. So Snowflake Intelligence is one of our first party agent products that makes it very easy for you to provide these like very generic natural language instructions like prep me for my Hyperloop meeting, or how many customers have open support tickets in the last 3 months. And then these will map down into SQL queries using LLMs.
So Ben, if I understand that this is the work that basically is doing NL to SQL translation. Is that the idea?
Yeah, that's pretty much it. One of the big key things here isn't just like identifying or is writing the SQL, but it's even knowing which tables to access. But yeah, that is the high level idea. And these features, we talked earlier about having access to query history and things like that. These benefit from that a lot. They have like a kind of a dynamic memory for seeing what types of queries users are doing, which types of interactions were successful and performant. And there's lots of kind of like few shot examples. It's tracking in its context and memory about which tables people use and how to access them efficiently.
Is this still work in progress, or is it being kind of is it available to your users?
Yes, this is generally available. I think it's evolving very quickly, but it is generally available already.
And what is the feedback that you have received from the users? Are they starting to use it extensively?
I think it depends. I think there's a lot of machinery in the background that makes this successful or not successful. And I think one of these things is there's these components, I think we call them semantic models, for identifying which tables are actually useful and how to use them properly. If that is well constructed, then I think this is a very powerful feature. But if those aren't provided, then the results can be pretty mixed. Yeah.
So could you, I mean, is it possible to, as you're prompting the system to generate the corresponding SQL query, underlying SQL query, at the time of the prompt, can you say that I'm looking for this information and the corresponding tables is this, this, and this. So if you do say that, then it helps the system formulate the query. I mean, does it work?
Oh, yeah, absolutely. If you provide the target tables, it will, I think, typically do a very good job. I mean, it depends on the complexity of your analysis, but if it is just like a simple query, like adding like group by this, or you don't even have to tell it to group by. You can ask a simple query, and if it knows which tables to look at, the SQL it writes tends to be very good.
And this you may or may not be able to answer. Sort of when so the underlying model that is being used to do this translation process from NL to SQL, do we know which one is more effective? Is it the OpenAI? Is it the
I think
which one works well, or is it all context dependent?
I think it's less context of it than like cost, like willingness to pay. Like I think the Opus and Claude models are doing very well here. Yeah, we also use a lot of the Chat GPT models. I mean, this is a landscape that's changing very quickly, but we have definitely found when we were doing AISQL, we were using Llama almost exclusively because we were self-hosting and we had access to these models, and they also have absolutely enormous margins because they're open and there's no like profit sharing or like but the quality of the models now, they're almost all gravitating towards these first parties, either ChatGPT or OpenAI, or sorry, or Anthropic.
So I mean, Fuhang knows about this. That there is a something called leadership board or something like that, which maintains people
Arena?
marks and then running, positioning them as to what percentage of, the accuracy they get in terms of the translation. Has Snowflake conducted those things? I'm sure they've done it internally.
Yeah.
You guys report those results on the leadership board or not yet?
Yeah, I don't think we have our own benchmarks. Actually, this is something that we've been talking about quite a bit. We have a few researchers in Poland, and we've been discussing creating our own benchmarks. There's an existing benchmark published by BigQuery called SemBench that we've been tracking quite a bit, and it's mostly about like querying databases with LLMs, but very similar to what we've been describing. In terms of like model quality itself, I think it feels like the standard is to just check Arena. So we don't publish our own versions of that. We, for a while, had our own internal benchmarks, or not even benchmarks, but like competitions, let's say, across different model types for like AI classify, AI filter. But I think this is moving so quickly that it doesn't feel like it's a good exercise to manually have a bunch of researchers or even junior engineers spending time evaluating which model is the best, what's the Pareto frontier on quality and cost. It is kind of increasingly either run an agent to do this for you or trust existing like leaderboards like Arena.
Yeah. Thank you.
Sure. Okay, so that's Snowflake Intelligence. There's a lot of other stuff we're doing on kind of the layer below that, like of all the agents we could be serving, or of all the agents customers want to build themselves. We have lots of tooling that we're working on, and a lot of these have already shipped on managing a large number of agents. So there's I don't think this is intended to be a customer-facing feature, but internally we have a lot of work on like this Uber agent for routing across all of your teams of agents. Being able to fork and spawn them and have them work in the background while you're communicating with like the head as this is progressing. And yeah, lots of integrations across different third-party providers or services you can work with. So lots of stuff. Yeah, a lot of the stuff on the SQL side is slowing down quite a bit. There's a big announcement coming tomorrow, so stay tuned. That's going to give a lot more detail on this. But we're putting into public preview some things on for having a support for web search, deep research, agent memory, agent skills, and things like that. And yeah, another thing coming is better control of memory management. This is becoming kind of a key focus area for Snowflake as well. So we talked a little bit about this Snowflake Intelligence project. Given the right tables, if you provide a hint, it'll almost always write perfect SQL. It may not be the most performance, but for an analyst who doesn't, or for even like maybe a business executive who doesn't know the SQL best practices, it will do a very good job of writing good SQL to answer a high-level business question. But the hard part of this is really identifying which tables are actually meaningful and useful to look at, which one has up-to-date data that is accurate. And this like ontology and history is kind of the key component to make that possible. Okay, I think that's everything I have. Thea, thank you so much for your time. Again, all this content came from this paper, Cortex AI SQL Production SQL Engine, that is going to be presented at Sigmod this year on the industry track. And yeah, there's an accompanying blog. Well, thanks for your time.
Thank you, Gary. Are there any questions from? There's no question.
Yeah. So
Yeah, Jimmy,
okay. So but you
just speak a little louder. Microphone is far away.
okay, great. Can you hear me, Ben?
Yeah.
Okay, great. So you talked a little bit about performance, but that's mostly compare performance just within your own like optimization scheme. Can you compare the performance, say maybe it was like a traditional database, something like that?
Sorry, compare performance with what was the word you used?
Just like a regular SQL search, like without AI assistance, like do you see a big time difference, or?
It's hard to do like a pure apples to apples comparison because there's so many parameters that go into that. For like a regular SQL query, or let me go back to, I mean, this is very much like the customer is paying for all of the hardware. That's like Snowflake's original design is that all of the execution is elastic and scales independently of data. So if you want, you can get like like a triple XL large that's going to have like a terabytes of memory, and you can get a dozen of these if you want and execute a very large query quickly, but it's going to be very expensive. So like performance in isolation is hard to do a fair comparison with. It's just about how much hardware are you willing to put into it.
I think to answer Siemens' question, I think what he's asking is if you do a traditional query, you get a sub-second response or second. Whereas if you do a query that has an LLM filter associated with it, that probably will run in minutes or longer, right?
Yeah, okay, I see.
Answer to that question from my side would be is the functionality that you are enabling is very, very different. So the comparison, as you said, is not apple to apple comparison. I think that's kind of you're right. I think it's when you make an LLM call, the overhead is going to be significantly different than accessing data that exists in a table on your a database or a cloud. That would be the answer. So when there are several questions that are coming, but I would like to ask you kind of in the competitive landscape. I think the AISQL integration, at least when Juan was starting to interact with I went and read up on this. Are there other database companies who are kind of, and a year ago at least, it didn't look like anyone had this approach of doing the AI integration at the SQL level. Are you seeing other database companies like Salesforce or Oracle or others trying to kind of play a role in this landscape?
Yeah, I would say the closest thing we found is BigQuery, is that they've actually started doing this well before we did. They had a experimental API called Big Frames that was, it's basically the exact same interfaces as this.
So that's from
yeah, exactly.
Okay.
So that's very similar. A lot of the research that got us into this space in the first place came out of Berkeley, a paper called Lotus, and they're affiliated with, I think like loosely affiliated with Databricks, but in terms of like mature products, it feels like Databricks, they have things, but they're not investing that much into it, it feels like. I guess it's easier for them too, is something is in like their Python Pandas API. If they just want to introduce a new API, it takes them like a month. And it's a pretty low investment. It's just a cheap Python in like wrapper.
So-
Uh,
So I think people from a database point of view, they probably are looking at more as a user-defined functions or something like that. That's kind of how they are looking at it, is that if you want to go and access that, then you basically wrap it up as a UDF and integrate it with your system, right?
Yeah, definitely. That is always an easy escape hatch or option to do. To be honest, I think Snowflake is increasingly pushing towards making changes in that layer because it's so much just faster and cheaper, and rather than integrating into like the low level database components. Like I think we are working on a bunch of I talked about earlier how like AI filter is sort of just a managed system prompt, and that there is some optimizations we do in the SQL environment, but as far as like the MVP or what gets this product running is it's basically just a UDF. So one thing Snowflake is working on is how do we make it easy for customers to generate their own UDFs and do their own prompt tuning and optimization. So we're looking at DSPy and GEPA for that. And then in that case, the final artifact is just the new UDF that has a system prompt embedded inside of it.
Okay, there are a couple of contributions.
My audible.
Yep.
Okay, I sort of had a question about related to like this slide, the next one, and I'm not sure if I missed it if you were talking about it, but so there's like multiple different models here, right? I think you said that like the user can choose which one that they want to use. Is there like any kind of scheduling there where like the system sort of automatically picks some model based on like some kind of heuristics or anything like that?
Yeah, scheduling it's not complicated. It's basically just first in, first out queues. But the main things that we're considering is that if someone is running an absolutely enormous workload, these queues have like a fixed capacity. Like we're not going to put a terabyte of data in them and wait 3 hours for it to empty the queue. So it's really just about managing throughput and having queues that are sanely sized. Like the whole point of the queue is just a buffer to keep GPUs hot. They're not intended as like long-term durable data stores. So they're quite small. There's new stuff we're thinking about that hasn't landed yet, but all of these providers, OpenAI, Anthropic, have async APIs. So you can write to a file and expect a result back in like an hour or two instead of a couple minutes. That is another component where scheduling will become more important, but we haven't shipped that yet.
Go ahead.
So yeah, good.
Yeah, I had a question about the semantic join. So you showed an example where there were around 7 or 6 categories.
Yes.
But what if you have a lot of categories, like 1,000 categories and billion reviews? And for each of these reviews, you are passing 1,000 labels. So does this confuse the LLM? And I had a query that is a vector embedding, does a vector embedding of each of these reviews make more sense in this case of joining?
Yeah, look, I'll answer the vector embedding part first. I think we looked a lot at using like cosine similarity for joins. And yeah, the main benefit is that it's very, very fast. I think one of our concerns was that you can do that, but then the type of join you're doing is strictly a similarity join. If like this join has has an instruction attached to it. Is this review maps to a category? But some of the examples we've seen were like contradictory, like does this paper contradict this paper? And then a cosine similarity would maybe get you the exact wrong result. So we looked at cosine similarity joins, but we didn't do a lot of optimization there. There are a lot of existing Snowflake products that like there are I think like vector array objects that customers can already do this with. We don't need to expose a new operator to handle that. So you can already do cosine similarity in native SQL. But yeah, this is not that. This is a prompt-based, instruction-based LLM operator. Your first question about like category size, yeah, this there's definitely degradation. You know, if you had 10, like one, the task just gets harder the more categories you have. Like a binary classification task is always going to have, you know, typically going to have a higher F1 than you know, mapping to 10 categories. It's just the space of like outputs is much smaller. For this product, this automation, I think it's capped to something like 1,000. I mean, and it's just an artificial parameter that dictates like this may not be worthwhile rewriting this query into classification. Um, yeah, there's absolutely a degradation if you have too many categories.
Right, sorry.
Do you put Snowflake or your customers ever really have like worries about exposing maybe like an entire like thousands of columns or rows of your data to a company like Anthropic or OpenAI?
Yeah, one of the key requirements for most of these providers is that there's a like a feature called zero data retention. And so this is for like for enterprise customers, they're guaranteeing that they never use this data for training purposes. And that's usually satisfactory. There is a more extreme thing where, especially like let's say governments, like we have contracts with Department of Defense, and they may say they will not allow us to use Quen. So there's a lot of additional like model allow list, block list constraints that we also provide at the like account level. So that's absolutely a requirement. And sometimes we'll have a model allow lists and block lists, and some companies will go even further and say these LLM calls are probably not because of privacy, but because of costs. We're just going to block access to all of these features categorically. So there's also a notion of function RBAC, where certain roles are not allowed to use LLMs using any model. So we support that as well.
So if I understand you correctly, essentially the issue of kind of data retention or privacy of user data is based on the contractual agreement between sort of OpenAI and Snowflake and the user. So that's how it is being established. So
yeah, exactly.
Making a declaration that they will never retain any data or use this data for their internal purpose. That's how it's being established.
Yep. It's this feature called zero data retention that a customer can enable or disable. If it's disabled, it actually frees up. You have access basically to more GPUs because not every provider has that enabled for every single model, or there may be a larger pool of GPUs available if you do not enable it. But it is, yeah, a feature flag that we basically just pass on to the provider and expect them to respect.
Yes, I have a question about the model cascades. So how long do you run both the smaller and like larger LLM models like in parallel before you determine like, the confidence score difference is enough to like just pick one of the two?
I mean, this is a online algorithm it has an estimate for uncertainty, and not just like there's a picture here of like the uncertainty region, but each of these thresholds, T high and T low, both of those also have uncertainty estimates. And so if the task is really easy, then maybe after a few hundred samples, then we'll switch to the proxy model immediately because we've established that it, to some statistical guarantees that this is aligned with the larger language model. But the opposite case can happen too, where we'll find that this task is extremely challenging, or possibly even the labels appear to be random, or more likely the small model is incapable of matching the predictions produced by the large language model. Those will never converge, and will eventually, I think there's maybe even a fixed budget because you can go into a failure mode where you end up calling both models in perpetuity. So I think there's some fixed budget where we say, this isn't working, stop using the proxy model, just call the large language model. But the main, when it switches or does not switch is just a function of the difficulty of the task.
Any other questions? Yes, sure.
Yeah, so I had another question about the natural language to SQL generation. So let's say a company is trying to do natural language to SQL for its engineers, but they don't want to leak their schema to the public APIs. So what are the existing solutions to this problem?
Okay. So there's a lot of layers of like this metadata or semantic model about which tables are important. Those are created on a per account basis. So they're never public. They're only accessible to within other users at your account, like your company or things like that.
So that is internal to Snowflake. I mean, so essentially, kind of security of the metadata that is associated with that particular enterprise.
Yes.
Remains in the confines of Snowflake farm.
Yeah, not just Snowflake, but even your company's like private warehouse or yeah, like it's kind of like the equivalent of a VPC, your private cloud, that never gets leaked to other accounts.
I have a question. So for Snowflake enterprise customers, is there a use case for fine-tuning Snowflake's in-house hosted models instead of using like traditional RAG-based pipelines?
There is, yeah. There was a separate project, there's a separate product that's generally available called Cortex Fine Tuning, and it's exactly what you described. A user can provide a label set and a base model, and we can fine tune something for them. This project never got a lot of traction. It was kind of complicated to use. There isn't a significant overlap in people who are using Snowflake for like, let's say, more advanced use cases like fine tuning or training your own models or things like that. So it exists, but it didn't get a lot of adoption. So it's essentially kind of like deprecated.
Is somebody else who had okay, anything else? Well, Ben, we would like to thank you for giving us this presentation. I think it was very valuable to understand what is the current state of the art. So thank you very much. Hope to see you in person one of these days. Are you going to Sigma?
Yes, yeah. Are you going to be there?
Well, unfortunately, I will not be making it this time. It's there are two challenges. One of them is that the conference time is the same as last week of classes here. Not that my students will not miss me if I'm wrong, but I have some other personal issues.
No.
Are you doing the presentation at Sigma?
I'll share it with my co-author, Pavo.
Okay. Good luck and congratulations.
Yeah, thank you so much.
Time award for Snowflake. And that is actually is a very impressive accomplishment for a paper that appeared 10 years ago and now being classified as an influential paper in the context of industrial database design. Thank you.
Yeah, thank you so much for having me.
More. So I think okay, so I'm going to end this.